Okay, in this podcast we're going to talk about special cases of electron configurations, or what electron configurations allows us to figure out. It's important that you take out your periodic table as you follow along because you'll need it to understand what we're doing. First of all, what was not covered in the electron configuration podcast was the electron configuration of ions. And they're pretty simple to do. You start off by just determining the electron configuration of the neutral atom. You either add or subtract electrons to make the ion, and then you almost always end up, not always, but almost always end up with the noble gas shortcut. The exception to that will be the transition metals that can form more than one ion. Alright, so let's take a look at aluminum 3+. Aluminum is the same as neon with 3s2 and 3p1. If I have a 3+, that means I have lost 3 electrons. So if I lose 3 electrons, those are the 3 I'm going to lose, and I end up with just a configuration of neon, which is really why aluminum loses 3 electrons, to become more stable and to become most like a noble gas configuration with 8 electrons in the outer shell. And the closest noble gas to aluminum is neon. Let's take a look at one more. Let's take a look at the oxygen 2- ion. Oxygen is the same as helium with a 2s2, 2p4. If I have a 2- charge, I must have gained 2 electrons, so I add the 2 onto the 2p to make it 2p6. And now what I have is the same thing as a neon configuration. So pretty easy to do. Alright, there's another term you need to know, which is called isoelectronic. And when we ask about atoms or species that are isoelectronic, we're talking about species that have the same electron configuration. So let's go ahead and do a few together, and then I'll ask you to do a couple. So we want to know which of the following are isoelectronic. So let's take a look at the first group. So if I look at fluorine, I got my periodic table up. If I look at fluorine and I look at the periodic table, you know, fluorine is right here. So it's going to gain an electron and become the same thing as neon. And of course neon has a neon configuration. Sodium plus right down here is going to lose an electron and become like the noble gas before it, which is also neon. And then magnesium right next to sodium is going to also become just like neon when it loses 2 electrons. So A is isoelectronic. It's an isoelectronic series. Alright, let's take a look at B. So if I look at B, I have 3 elements that are not ions, neutral elements, and there is no way they are going to have the same electron configuration. So B is not isoelectronic. If I look at C, I have 4 different elements, all with a -1 charge. Again, just like B before it, there is no way that's going to be isoelectronic. They're going to have different numbers of electrons because they've all gained 1 electron. Okay, so C is not isoelectronic. Let's take a look at D. So here, D, E, and F, I'd like you to try. Okay, I'm going to pull those up. Okay, there are some atoms that where their electrons do not follow the rules. Kind of like a beaver over here. You know, there's a sign saying no feeding, and the beaver doesn't know what it says. It just knows what it wants. It's kind of like an atom. And contrary to the rules, there are some atoms that have electron configurations that don't follow the rules that have been established. But the facts always rule, right? So the facts are what determines what these are. So you'll see these exceptions only in large atoms. They are due to subshells being very close in energy. And the reason that they form these exceptions is always due to stability. They are more stable that way. So you don't need to know what the configurations are for specific atoms that don't follow the rules, but you do need to know that the reason why they do this is to become more stable. So let's take a look at copper. Copper has an electron configuration of argon plus 4s2, 3d9. So if we look at the orbital notation for that, what we see is the 4s is filled, and the 3d has all 5 of its orbitals filled with pairs except for one. So what happens is one of those s electrons gets promoted to the 3d9. So the 3d9, which is a little bit larger, higher in energy, ends up with the paired orbitals. So what we know here is that paired filled sublevels are more stable than partially filled. That is something that is always true. So an atom that has filled orbitals is more stable. Okay, so that's part of why that does that. Let's take a look at, let's take a look at, not copper, we're going to do chromium. We just did chromium. Alright, so chromium is the same as argon with 4s2, 3d4. And if I look at the orbital notation, I have a full 4s2 with a pair, and then I have 4 out of the 5 d orbitals have 1 electron each. So one of those 4s gets promoted into a d. Okay, so what we said earlier was the filled orbital sublevels are more stable than partially filled, but half-filled are more stable for an element like chromium, are more stable than having one that is unfilled. Okay, so if I had a configuration, a D configuration like this versus one like this, this would be, and I had one, let's say, like this. If I ordered them in terms of the most stable, this would be the most stable, this would be the second most stable, and this would be the third most stable, right? So those where they're completely filled is the most stable. Those where they're, each one has an electron is the second most stable, and those that have unfilled orbitals are the least stable. Alright. Alright, so we're going to talk about 3 terms, or 2 terms in a situation. One is paramagnetic and diamagnetic. So these are, they have magnetic in the term, but they're not the same as ferromagnetic, which is what iron is, which is the most magnetic, very strongly attracted to a magnet. Okay, but a paramagnetic is attracted to a magnet, and what causes it to be attracted is the unpaired electrons in the atom or the molecule. So all you need is one electron that isn't in a pair, and you have a paramagnetic atom. And the more unpaired electrons you have, the more magnetic you will be. Then the opposite is diamagnetic, and these are species that are slightly repelled by magnets, and this occurs when every electron has a pair. Okay? And then lastly, you can identify that if you have a solution of an ionic compound, an aqueous solution, and it's got a color to it, you will know that there is a transition metal in there. Okay? Not just a transition metal, but a transition metal that has an unpaired d electrons. And what causes the color, just like what Bohr talked about, is that those d electrons can get excited between the d orbitals, and as they do that, they release colored light. Okay? So let's take a look, see if you understand this. Alright, so the first question and the second question, I want you to pause and then go ahead and answer them. Okay, that's going to do it for us.